In this video lecture, we have to talk about mechanics of a system of particles. Consider a system of n particles. The first particle of mass m1 is at a distance r1 from the origin. Ith particle of mass mi is at a distance r suffix I from the origin. Capital R be the position vector of the center of mass of the system. The value of R is given by m1 r1 plus m2 r2 then mn rn whole divided by m1 plus m2 then mn. This is summation mi ri divided by summation of mi. Here the value of I equal to 1 to n. Here also the value of I equal to 1 to n. This is 1 divided by capital M into mi ri. From this m capital M into capital R equal to summation mi ri. M is the mass of the entire system and capital R represents the center of position vector corresponding to the center of mass of the system. Now we have to prove that the linear momentum of a system is constant if no force is acting on the system. For that, consider the force acting on the ith particle. F suffix I denotes force acting on the ith particle. Ith particle may be first particle or second or whatever it may be, because the system is having n number of particles. This is equal to Fi external plus summation of j Fj internal. Consider this is equation 1. If you consider an individual particle, say the ith particle, the force acting on the ith particle is equal to external force plus the contribution from the internal force. In order to understand more about the second term, consider the system is having at least 3 particles. Then Fji equal to, if you assume first particle is our ith particle, the remaining 2 particles, that is the possible values of j are 2 and 3. Now Fji is F21 plus F31. The second particle applies some force on the first particle. Here the third particle exerts some force on the first particle. These 2 forces are contributing to the internal force term. Suppose the system is having only 3 particles. Therefore, the force acting on the ith particle of the system is given by contribution from the external force plus the contribution from the internal force. Then, for the entire system, if you want to know the external force acting on the entire system, just take the summation. Here I equal to 1 to n. On the right hand side, we have to write Fi external, and also I equal to 1 to n. Here the second term, the summation, let's put I comma j, then fji internal. Here I not equal to j. This is a force acting on the entire system. According to Newton's third law, Fij equal to minus Fji. Therefore, Fij plus Fji equal to 0. The force acting on the jth particle due to the presence of ith particle is equal to force acting on the ith particle due to the presence of jth particle with opposite sign, which means the two forces are equal in magnitude but opposite in direction. Therefore, the summation of these two provides 0. As we pointed out earlier, suppose the system is having 3 particles, we can consider 3 possibilities. I equal to 1, then j equal to 2, 3. I equal to 2, then the possible values of j are 1, 3. I equal to 3, then the possible values of j are 1, 2. With the help of these 3 possibilities, we can write down Fji, which is equal to, take this first possibility, F21 plus F31. For this possibility, we may get 2 forces. And consider the second, F12 plus F32. Then for the last case, F13 plus F23. These are the 6 possible forces contributing to the second term, that is internal force term. But according to Newton's third law, Fij plus Fji equal to 0. Consider this F21 plus F12, the value is 0. F31 plus F13, 0. F32 plus F23, 0. If you consider the entire system, the contribution from the internal force term is therefore 0. But if we consider a separate particle, individual particle, the contribution from the internal force term is acceptable. But if we enlarge to the entire system, then the contribution from the second term, that is internal force term, is 0. Now, the above equation is modified as, for the entire system, summation of I equal to 1 to n f suffix I, which is equal to Fi external alone. This is simply written as F external. Say this is equation 3. According to Newton's second law, rate of change of momentum is force. dP by dt equal to F external. Now we may lead to a conclusion. If F external is 0, that means no force is acting on the system. If F external equal to 0, then dP by dt equal to 0. This gives P a constant. This linear momentum of the system is conserved. Now we may write a conclusion. In the absence of external forces, the linear momenta of a system of particles remains constant. This is the first conclusion we have arrived. If no force is acting, linear momentum is conserved. Now we may approach the same problem in terms of center of mass. See here, according to Newton's second law, dP by dt equal to F external as far as this case is concerned, but P equal to m into v. Linear momentum equal to mass into velocity, which is m r dot. R dot is our velocity. Then we may write d by dt of summation mi ri, which is equal to F external. For the entire system, external force equal to d by dt of summation of mi ri. This ri single dot, because rate of change of momentum is our force, mi ri dot is our p. d by dt of ri single dot is ri double dot. Then we can write mi ri double dot equal to F external. See this relation, mi ri is equal to capital M into R. M is the mass of the system, R is the position vector of the center of mass. Now we can write M into R double dot is equal to Fe. This M into d by dt of R single dot equal to Fe, where R single dot equal to velocity of the center of mass. Now we may get another conclusion. If Fe equal to 0, if Fe equal to 0, that means external force acting on the system is 0. M into dr dot by dt equal to 0. Therefore, r dot equal to constant. R dot is our velocity of the center of mass. Now we read the second conclusion. In the absence of external forces, in the absence of external forces, the velocity of the center of mass of a system of particles remains constant. This is the second conclusion we have arrived. If no force is acting on the system, the linear momentum of the system remains constant. If no force is acting on the system, the velocity of the center of mass of the system remains constant.